we have a change of x. This is a problem on the homework. We have some angle given. I'm going to do it to where it really doesn't matter what the angle is. We have some initial velocity, I don't know. But it is a two-dimensional problem, so let's set up the x's and y's. V naught, Vf, A, T, delta x, and delta y. And so I don't really know where to go with this problem, but I know that I really want to find Vx. So whatever the numbers is supposed to be there. I'm just going to write down Vx because that is actually what I want. And I know I'm never going to get it until I'm actually done with the problem, so I'm just going to write that down. We know that the Vx does not change because the acceleration is 0. In this problem, I believe we would know how far over you went, but I'm still going to keep it as a variable. So I'm just going to say the delta x. That's kind of redundant to do that. In the y direction, we know that we start off with some velocity vy, and it has an acceleration of negative g, or 9.8, and that's the way we look at the delta y there, and that's going to be 0. If we jump off the ground and reach back to the ground, that means gravity was slowing it down and speeding it up on the way up and down. So my velocity Vy should be the same thing at the end, but just negative, and that's because we have 0 displacement in the vertical. And that actually helps us out a lot. So in the x direction, I know that there's only one really good equation to use, which is this one. And remember, we really wanted this velocity in the x direction. We are given some value x in the problem, which I'm still going to keep as a variable. But in order to solve it, we really need to replace t with something. And so we're going to go to the y direction. I'm going to attempt to use the same equation, which is the third one, which says the delta y is equal to the velocity in the y direction to start times the time plus 1/2 the acceleration times the time squared. And I really need time. So I could use this equation and plug stuff in, but I'm also going to notice that I have another equation that does have time that's a little bit simpler than this one. It's going to get the same result, but I'm just going to run straight to that, and that's the one where it says final velocity is equal to initial velocity plus acceleration times some delta t. Again, both equations are going to get us the same answer, but this one looks a little bit easier for time. Final velocity in the y direction is just negative Vy. Initial velocity in the y direction is just, we're going to call it Vy. I know that some of you are going to be like, but it's V naught sine theta. True, but you'll see why in a second. We're going to have minus g delta t for the acceleration and the time. And so to solve for time, I'm just going to move this Vy to the left side, which is going to be negative Vy minus another Vy. And then we're going to divide by negative g, and that gives me negatives cancel out, so 2 Vy on top divided by g on the bottom, and that would be my change in time. And I wanted that to use right here, so I'm going to plug it in right up here. We're going to move down, give myself some more room here, taking that equation, bringing it on down. The delta x is equal to the velocity in the x direction times this thing that we call time, and in parentheses we're going to write down 2 Vy over g. Okay, because that's what we just solved for over here. So we're going to plug that in. We're going to look at this a little bit. We know a value for x in the problem. We really want this though. And g we know the value of. Vy we really don't know the value of because we don't know the initial velocity v naught in the first place. So maybe we can set Vx and Vy in terms of each other. And to do that, we're going to remember that the initial velocity is just a triangle. It's a vector. And this is Vy and this is Vx in the beginning, and this is some angle theta. Well, what trig function relates Vy and Vx? Opposite, adjacent. That's going to be tangent. Tangent of theta is equal to Vy opposite over Vx, the adjacent. And let's solve for Vy, move the Vx over. Vx tangent of theta is equal to Vy. And that's good because now I can just put it in right over here. And the change of position x is equal to Vx to, well, all that stuff. Vx tangent of theta, okay, divided by g. And we're in a pretty good spot. Let's move the g over. G delta x, let's move that 2 over. over 2. And let's also move that tangent over, tangent theta. So we just divided those guys to get them to the other side, and that's left with Vx twice, which is Vx squared. Well, how do you get rid of a square is when you square root. So we need to square root g delta x over 2 times the tangent of the angle. And that should give us the velocity in the x direction. And that'll finish up the video.